again, like I just said, target one, it's about taking two functions and either putting them together with addition or subtraction or multiplication or division, which whatever feels right to do in the situation is probably right. Your intuition is going to be right. If you think you should FOIL, you probably should. If you think you should distribute, you should, etc. It's the last part, composite function, that's the weirdest, taking two functions and putting them together so that one of them is actually plugged into the other. And it's all about efficiency. Like if you're a computer software programmer or you use a computer, you want your machine to be as efficient as possible. You don't want it to lag and it to take a step that should take 2 steps and it take 5. So this is what this target and its back is about, taking two things and making it one. Probably the first thing we need to talk about is the symbols. The symbols. And in this chart, you can see all of the symbols of taking the function f and the function g and putting them together according to this addition. You're going to take the function f plus g of x. In that order, you're going to take function f and function g and add them. Addition doesn't really matter. 2 plus 3 is 3 plus 2. But subtraction, it does matter. 2 minus 3 is different than 3 minus 2. So you just pay attention to the order that the letters are represented, but you're going to, in subtraction, take your f function, f minus g of x, and subtract the 2 in that order. It's pretty intuitive, but let's take a look at a couple of problems. The domain and range definitions that we discussed yesterday are up there. We will need them. Okay. Example 1. You're always going to be given a function f of x and g of x, and sometimes even more, but they're going to tell you what f of x is, what g of x is, what h of x is, or whatever letter, okay? But then the directions here say find f plus g of x. So to find f plus g, you take the f of x function and you add the g of x function. Pretty intuitive. You take the 4x plus 7 and you add the square root of x plus x. With addition, those parentheses that I just put really don't matter, right? When you're adding things, you add the like terms. With subtraction, it will, so that's why I'm putting them there. But when you add that 4x and that x, that's the only like terms, you get 5x plus the square root of x plus 7. And it doesn't seem like much, but you've just taken two functions and made it into one. You've taken g of x and f of x and you put them together. Now let's take f minus g of x and find it. That's f of x minus g of x according to the template, which is intuitive. Take the f function and subtract the g function. F of x is the 4x plus 7 and subtract, so in parentheses, subtract the function g of x, which is square root of x plus x. We really should be having a much deeper conversation here about why we're writing 4x plus 7 and square root of x plus x instead of the symbols g of x. We should be having a very domain and range discussion. When you plug x into f, you get 4x plus 7. When you plug x into g, you get square root of x plus x. So that's why I'm taking the range values and subtracting them, or the range values and adding them. But we're going to save that a little bit more for the back of the worksheet, more of a domain range discussion. But the like terms here are the same as they were before. It's just when you're subtracting g of x, this becomes 4x plus 7 minus the square root of x minus x, and your like terms become 3x. 3x minus the square root of x plus 7. So last period, I didn't foresee this, but the question came up last period, so I want to address it here. That's not an equation. That's a function. It's an expression. So you're bound by those rules of distribute and combine like terms, or just put things together any way you can, okay? But there's no equals 0. And you're not going to say the answers are x is 0 and x is 7, or right? It's just an expression. You have rewritten and found the new function f plus g of x, and it is 5x plus the square root of x plus 7. You wrote a new function, okay? And over here, you wrote a new function for f minus g of x, and it's 3x minus the square root of x plus 7. Now, what are the domains? What are the things you plug in to the function? Well, you need to look at the original functions and the composite, or not composite, wrong word, combined function. What is the domain for the 5x portion of the new function? Can you put anything you want into a 5x? Yeah. Can you put anything you want into the square root of x? Think back to yesterday. Can you put anything you want? That's what the domain question from yesterday was. What are you allowed to plug in for x? What are you not allowed to put in under a square root? A negative. So your domain is going to be restricted by that square root to greater than or equal to 0. Okay, so the domain for this combined, I'm using the wrong word. The domain for this combined function is restricted to x is greater than or equal to 0 because of that square root of x. So the other one, the f minus g, I could plug anything into 3x. But again, I'm restricted by the square root. The domain is just x is greater than or equal to 0. Again, yesterday we talked about domain a lot more intensive. That video is worth watching if you weren't here. Hopefully that jogs the memory. I don't think I need to really explain a whole lot more about this process. It's take the function f and multiply it, or take the function f and g and subtract them. It's follow the order that it's given. So what would you do in this next example, f times g? You take f of x and g of x, take their ranges, and multiply them. So what comes to mind when you take x squared minus 9 and x plus 3 and multiply them? What comes to mind when you're multiplying those two things? Do I need to write it on paper? F times g of x, according to the table, is just take your f of x and multiply it by your g of x. And again, we should be having a much deeper conversation, and we're kind of getting there. If I put x into f, what comes out? If I put x into f, what comes out? This comes out. That's the thing that comes out, x squared minus 9. So the x squared minus 9 gets multiplied. When you put an x into g, what comes out? X plus 3. So you multiply it by x plus 3. Now what comes to mind? That's what I was visualizing. It was too early for me to ask that question earlier. What comes to mind now? FOIL, right? So FOIL. This is the only algebra intensive portion. I mean, it's not that bad, right? X squared times x is x cubed. X squared times 3 is 3x squared. Negative 9 times x is negative 9x, and negative 9 times 3 is negative 27. And you found the combined function. Division. We'll come back and do domain after we get this one on the page 2. Division. F divided by g of x is literally f of x divided by g of x. Take the function f of x and divide it by g of x. Well, that would look like x squared minus 9 in the top divided by x plus 3. Can you do anything with that? And the answer is yes. We had a whole unit last unit that had those. Can you factor the top of that fraction? Would it cancel? Then we should. You factor the top, x plus 3, x minus 3, and those x plus 3's cancel. So your final answer is just x minus 3. The combined function f divided by g of x is x minus 3. All right, now let's answer domain. What is the domain of each? So let's explore all three, the f of x, the g of x, and its combined answer. What's the domain for f of x, a quadratic? What's the domain for an x squared minus 9? What can you plug into that? Anything, right? What can you plug into x plus 3? Anything. And then the composite was an x cubed, a polynomial. What can you plug into a polynomial? Anything. So the domain is all real numbers for the multiplication of these two. But what about the division? You got to be careful. If you only look at the end, it's kind of like excluded values. If you only look at the end, you're going to say all real numbers, right? But if you look at the beginning, you also might say all real numbers. because the quadratic was all real numbers, the linear was all real numbers, f and g. But what happened as soon as you made a fraction out of them? You can't put what in? I heard it over there. Can't have a 0 in the bottom, so you can't put -3 in for x. So you got to look everywhere. So the domain is almost all real numbers. It's everything, all real numbers, but x cannot equal -3. As interval notation, it would have looked like -infinity to -3, not including -3, union with -3 to infinity. Just another way to say what we just said verbally, any number but -3. Like, that's the easy part. Would you agree that was pretty straightforward? Pretty easy? Some of you so much that I can see you're getting a little distracted. I can feel it. Got to come back together because this next part is very confusing. I promise. Okay? Nothing hard about it, just conceptually challenging. All right? To warm it up, I've got this little slide that you don't have. It's really quick. If you have the function f of x equals 2x, if you have the function f of x equals 2x, and you put a 5 into that function, a 10 comes out, right? So for that one example, putting a 5 in and a 10 comes out, what's that specific domain? What's the specific domain on the left side here? The thing you plug in, 5. What came out when you put that domain value in? 10. This is where it gets challenging. What's the actual domain of f of x? X. The actual domain is x. Anything you want to put in for it's x. What's the actual range? The thing that comes out, you double the thing you put in. 2x. Your range is the 2x. Okay, and in the front page of our notes, we were adding those ranges or subtracting those ranges or dividing or multiplying, okay? It gets pretty tricky on the back though. All right, last part. Composite functions. I'll try to use this example again. A composite function is kind of like this. If you're working on an assembly line and you're making a product, say you're making crackers. Go with crackers, okay? The first thing you're going to do is take the products, the dough, take the ingredients and put it in some machine, and what's it going to do to that dough and that ingredient? What's it going to do? It's going to make a cracker, right? Now, is it done? Are they going to put it on Walmart's shelf as a cracker? No, they're going to take that cracker off of this assembly line, take it over to another assembly line, and it may be the same one, but it's a different machine that does what to that cracker? Well, it puts a bunch of them together and puts a package around them. Then after that machine's done doing what it does, it takes that sleeve of crackers over to another machine and makes a box for that sleeve, and then they put it on the shelf, right? All right. What I'm talking about is domain becomes range, becomes domain, becomes range. You started with dough. It became a cracker. Then you take that output and put it into another machine, and it puts a sleeve around it. Then you take that output and put it into a third machine, and it puts a box around it, and then you have a finished product, right? That's what a composite function is. You take something, put it into one thing, it does something to it, and an output comes out, and that output becomes what you put in to the other. All right, here's what it looks like on a picture. The symbols are very similar to time. Notice the difference. What's the only difference between the F times and what we're doing here? An open circle. This F open circle, you read it out loud this way. F of G of X. F of G of X. The way I like to look at it, F of G of X. I like it in that symbol. So even if it has an open circle, I'm going to change it to that blue symbol because it looks better to me. Okay? And here's what it means. Take your X. This is what the picture is showing you. Take your input X, take your dough, and put it into the machine that makes the cracker. So that's the X. I need to do this on the screen since I'm recording this. Take your X, and it's the domain, it's the dough, it's what you put into the first machine. The machine turns it into something, a cracker, and you put it into another machine called F, and it turns that cracker into a sleeve. You get what I'm saying. We're only going to be dealing with 2 machines. We won't be dealing with 3 machines or 4, although we could. All right? Now let's try some. All right, I've switched your option 1 and your option 2. because option 1 should be what's on the right. Option 2 should be the one on the left. So your notes need to change just a little. Given these two functions, f of x and g of x, what is, that shouldn't say are, what, I was going to do more than one and I didn't. What is f of g of -3? We're going to do option 1 over here, aka f of g of -3. When you heard me say that, you probably heard the same exact thing, right? F of g of -3 and what I just put a box around, they're the exact same thing. But I'm going to always write it as f parentheses g of -3. I'm going to write it that way because it just looks better to me. Okay? Now here's what it's saying. Take -3, put it into g. Take -3, put it into g. You can do that mental math. What do you get when you put -3 into g? G of -3 is -3 squared. It is 9. That's the cracker. The 9 it's the output of g, but when I put it back into this situation, it becomes the input of f. In other words, I replace g of -3. I replace g of -3 with that 9. So now 9 is the input into the other function f. And when I put 9 into f, f says take your number and subtract 5. So take that 9 and subtract 5. So this becomes 9 minus 5, the final answer, 4. With numbers, it's pretty easy. Once you do a few of these, it's pretty straightforward. It's the variable part that's tricky. All right, so I'm going to teach this different than I did last class. I'm going to stop right there with option 1 and go to you trying a couple of these at the bottom and then come back to the hard part because I tried to do it all last period and I don't think it was as effective. So let's just pause the video after I explain what I want you to try on your own. You've got 3 functions, f of x, g of x, and h of x provided here at the bottom. I want you to try 1, 2, 3, and 4. Notice they're all just numbers. Okay? And I'm going to get you started on number 1 just by rewriting it. If it's in that order, F, O, G, it's F, open parenthesis, close parentheses, and inside of that parenthesis, G of -1. All right, now I'll pause it and let you try. Now I'll walk around just to kind of see how it's going. See a little mixed results. That's why I'm working it, okay? I'm seeing a lot of 8s, the answer being 8, but I'm seeing some that are struggling with it. So for starters, focus right here. And I'll even try to get the same color there. G of -1 is telling you take -1, go to the function g, the middle function, and put in a -1. When you do that, g of -1 gives you 3 times -1 plus 5, it gives you 2. So your input of -1 gives you an output of 2. That output value of 2 becomes your input into a different function, f. So now the directions are saying take your 2 and put it into f. So go up, find the function f, got it, and put a 2 in for the domain value. 2 squared, 4, plus 2 times 2, 4 plus 4 gives you 8. All right. Hopefully that'll help you get in the right direction on number 2, 3, and 4. So I'll pause the video again for those that were struggling with number 1. It's okay, it's a new topic, but try 2, 3, and 4. I'll go ahead and tell you the answers. 2, 3, and 4. The answers for 2 should be 50. 3 is 5 over 4, or 1.25. And number 4 is 11. All right, number 2. The first thing you need to focus on in number 2, and I'll try to keep the colors the same, it's telling you to find f of -3 first. So you go up and find the function f. Find the function f. the yellow one, and you put in that 3. When you put a 3 in, it's 3 squared plus 2 times 3. What number does it become? The number becomes 9 plus 6 becomes 15, right? So that 15 replaces the f of 3. So now you're tasked to find g of 15. So go find the g function. It's in the middle. And put a 15 in. When you put a 15 in, it's 3 times 15 plus 5. 3 times 15, 45. Plus 5, 50. And that's how you get the final answer, 50. H of 1. H of 1. Go up to the function h and plug in a 1. 1 over 1 plus 1 is the number 1/2. 1/2. So now you're going to find f of 1/2. If you take f and plug in a half, you get a half squared plus 2 times a half. And mental math, you might be able to do that. What's a half squared? It's a half squared. Now 1/4. 1/4. What's 2 times a half? 1. So 1/4 plus 1 is $1.25. So you can either write 1.25 or the fraction is 5 over 4. And the last one with numbers, g of, and I see if I just change colors, g of -1. That's what this is saying with that open circle, g of -1. So start by taking a -1, putting it into g. I think you're almost to the point you could probably do just mental math with this, right? I hope. When you plug in a -1, right there and there, what do you get? 3 times -1 plus 5. You get 2, right? So that blue part becomes 2. Now it's saying go back to function g, put 2 in. And that gives us 3 times 2 plus 5 gives us 11. 3 times 2, 6, plus 5 gives us our final answer of 11. All right, and I'm going to stop the video right there because that's the numerical side of composite and the easy. This last part, I'm doing it separate so that if you need to go back and watch it, you can go back and watch.